Everyone, my name is Vihar and I'm currently a grade 12 student with a deep interest in astrophysics, quantum physics, and aerospace sciences. Today I'm excited to present one of the most fascinating ideas in the modern physics, the unification of forces. We'll explore how the four fundamental forces govern everything in our universe, from the smallest subatomic particles to the largest galaxies, and how scientists are working to combine them into a single elegant theory. In this journey, I'll be taking you from the exact point of the Big Bang or the start of universe to to the point where we currently are. So let's begin the incredible journey into the fundamental laws of nature. Beginning with the first fundamental force, the gravity, the force that shapes the universe itself. Gravity is the attractive force that exists between every object with mass or energy. If you have mass, you produce gravity. Even you are pulling the earth towards yourself, but because earth is so massive, only the earth's pull is noticeable. Unlike some forces, gravity never completely disappears. Its strength keeps decreasing with distance, but it technically extends across the entire universe. Gravity is incredibly weak at the particle level, yet it dominates the universe because it only attracts but never repels. Every object with mass contributes towards gravitational force. It affects and accumulates over enormous distances. Without gravity, stars wouldn't form, galaxies wouldn't exist, planets wouldn't orbit the stars, we wouldn't stay on the earth. As per Isaac Newton, he proposed that every mass attracts every other mass. The bigger the mass is, the stronger the attraction. The farther apart they are, the weaker the attraction. This is proven by the mathematical law, which is widely famous. While Newton imagined gravity as a force, Einstein said that gravity isn't really a force. Instead, mass bends space and time. Objects simply move along the curved space time. Imagine placing a bowling ball on a stretched rubber sheet. A marble rolling near curves toward it. Not because the bowling ball is pulling towards it directly, but because the sheet is curved directly. The rubber sheet is an analogy for the space-time, the only fundamental force that has been not yet successfully unified with quantum mechanics. Physicists are searching for a quantum description of gravity which may involve a hypothetical particle called the graviton, but it has never been detected. This is one of the greatest unsolved problems in modern physics and a major motivation for theories like quantum gravity and string theory. Gravity is the weakest force of nature's four fundamental forces, yet it is the sculpture of the cosmos. It gathers gas into stars, binds planets into orbits, shapes galaxies, and creates black holes. Newton showed us how gravity works, while Einstein revealed why it works through the curvature of space-time. Even today, gravity remains one of the deepest mysteries in the physics because we still don't know how to fully unite it with the quantum world. Moving on to the electromagnetic force. Most textbooks define it as the force between electrically charged particles. That's correct, but at the same time, it's incomplete. Deeper definition is electromagnetism is the interaction that arises because the charged particles exchange photons through the electromagnetic field. Notice I didn't say through empty space. The field is fundamental object. Particles don't pull on each other instantly, they interact through the changes in this field. The source of electromagnetism is the electric charge. Charge is one of the fundamental properties of matter. Just like mass or spin, there are only two types of charges, the positive and the negative charge. Unlike mass, gravity only attracts. Electromagnetism both attracts and repels. This simple fact makes electromagnetism far richer and vast than gravity. But a curious mind would always ask, why do moving charges create magnetism? This is one of the most profound ideas in physics. Imagine standing beside an electron. If it's stationary relative to you, you observe only an electric field. Now imagine the electron moves. Suddenly, a magnetic field appears, but there's the surprising part. Another observer moving with the electron may see only an electric field because, as per his frame of reference, the electron would be at rest. Magnetism can be understood as the consequence of special relativity. Electric and magnetic fields are different aspects of the same electromagnetic field. This was the overview that Einstein provided. And different observers can disagree on how much electric versus how much magnetic a field is. The complete electromagnetic force on a charged particle is given by the Lorentz force. Talking about the Maxwell's great unification theory, before Maxwell, electricity and magnetism were separate subjects. Maxwell combined them into four equations. These equations say charge creates electric fields, magnetic monopoles don't exist as far as we know, changing magnetic fields create electric fields, changing electric fields can create magnetic fields. This last insight was a revolutionary topic that Maxwell put forward. This changed our understanding towards modern physics and also opened gates for many new possibilities. A changing electric field can create a magnetic field. The magnetic field changes, which creates another electric field, and so on. This self sustaining cycle travels through the space. The Maxwell's astonishing prediction was that light isn't a substance. Light is a self propagating electromagnetic wave. An oscillating electric field and an oscillating magnetic field regenerate each other as they move through the space, and so the light does. Classical electromagnetism treats the field as smooth and continuous. Quantum theory reveals something more deeper. The electromagnetic field is quantized. Its smallest excitation is the photon. Charged particles interact by exchanging virtual photons, while real photons are what we can't detect as light. QED is one of the most accurate theories ever developed, with predictions matching experiments to extraordinary precision. This proves that electromagnetism is yet another force which has always made a human mind curious to explore more. Let's dive into the two nuclear forces, the strong nuclear force and the weak nuclear force. These are the two type of forces that operate deep inside the atomic nucleus and at the smallest scales of the nature. The strong nuclear force is the strongest fundamental force in the universe. It is the force that holds the quarks together inside proton and neutrons and indirectly holds the nucleus together. We know that a proton contains of two up quarks and one down quark, while the neutron contains of one up quark plus two down quarks. The problem arises, why doesn't the nucleus explode? Nucleus contains protons, the positive charge, and neutrons, the neutral charge. Protons repel each other because they have the same electric charge. Two protons, they should push apart due to the electromagnetic repulsion. So why does a nucleus stay together? Because at extremely tiny distances, the strong force becomes much stronger than the electromagnetic repulsion. It acts like a powerful nuclear glue. Diving deep inside the stronger force, there are gluons. They are massless particles. They carry the strong interactions. They glue quark together. There are eight types of gluons. The theory describing them is known as the quantum chromodynamics theory or QCD. But the strong force shows a very strange nature. Unlike gravity and electromagnetism, it gets stronger when quarks move apart. Imagine two quarks connected by a rubber band. Pull them apart, the force increases. Push them closer, the force decreases. This property is called as confinement. Quarks cannot exist freely alone. Talking about the range of strong force, the strong force is extremely powerful but a very short ranged force. The range is about just the size of a proton. Moving on to the weak nuclear force. The weak force is responsible for various activities like radioactive beta decay, nuclear fusion inside stars, and even transformation of particles, which means it can actually change one particle into the another. But what actually carries the force? The carrier particles are called as weak gauge bosons. They are very massive. The W boson and the Z bosons are the carriers for them. Because they are heavy, their range is extremely tiny. Range of weak force is approximately more smaller than the nucleus. Even if it is called as the weak nuclear force, but without it, the stars wouldn't shine, the sun's fusion process would entirely stop, many elements would neither form. But even though it is known as the weak nuclear force, it is not as unimportant as it sounds. It is called weak because it is compared to the stronger nuclear force. But without the weak nuclear force, the stars wouldn't shine, the sun's fusion would entirely stop, many elements would never form. Crucial part of this session. This is where the physics transforms itself from studying the nature to asking one of the deepest questions ever. Can the entire universe be described by a single force? This idea is called as the unification of the forces, and it is one of the greatest unsolved problems in the modern physics. This is the part where we actually travel from the exact point of Big Bang towards its end and study how forces shaped itself into the forces we see today. Imagine the universe at its birth. Close your eyes and imagine the universe just 10 raised to power minus 43 seconds after the Big Bang. Not a second, not a billionth of a second, but actually a decimal point followed by 42 zeros before you even reach the number 1. This tiny instant is called the Planck epoch. Now ask yourself, did gravity exist? Did electromagnetism exist? Did the strong and weak nuclear forces already exist? The surprising answer is probably not. Physicists believe that all forces were tightly packed and once different expressions of a single fundamental interaction. Think of a white light. White light looks like one color but pass through it through a prism. It splits into seven colors. The early universe may have worked the opposite way. Today we see four forces, but rewind time, they merge into one. But why do physicists even think of this? It is because nature loves symmetry. Whenever we discovered something that looked different, eventually we realized that they are actually connected. For example, electricity and magnetism were once thought to be unrelated, but then James Maxwell showed they are two sides of the same electromagnetic field. That success inspired physicists to think if two forces can unite, why not all the four forces? This takes us to the point of the cooling of universe. As the universe expanded, it cooled down. Think of it like cooling of a molten metal. When it cools, crystals form, different patterns appear. Similarly, as the universe cooled down, the perfect symmetry of the original force broke. This is called spontaneous symmetry breaking. One force became many. Moving on to the stage first, the ultimate force. This is the exact time of the Planck epoch, the 10 power minus 43 second mark. The temperature was at around 10 raised to 32 Kelvin. Everything was unimaginably energetic. There were no atoms, no protons, no neutrons, no quarks as stable particles, no photons behaving normally. Space and the time themselves were probably fluctuating quantum mechanically. Gravity was not separate, neither were the other forces. There was only one unified force. But unfortunately, we don't yet know its mathematical description. This is why physicists search for a theory called theory of everything. Coming up to the stage 2. This is where gravity separates. At the end of Planck epoch, gravity becomes independent. The remaining forces stay united. This hypothetical force is called the grand unified force. Now we have gravity as a separate force, while the other three as grand unified forces. But why did gravity split first? Nobody knows for a certain reason. Gravity is incredibly different from other forces. The other three are described as quantum field theory. Gravity is described by Einstein's general relativity. These two frameworks don't fit together at Planck scale energies. That mismatch is one of the biggest challenges in theoretical physics. Moving on to the stage 3. The strong force separates. About 10 per minus 36 seconds, the temperature was around 10 per 29 Kelvin. The grand unified force broke again. It broke its symmetry. Now we got the strong nuclear force and electroweak force. This is the era explored by grand unified theories. But what exactly is grand unified theory? This theory attempts to show that strong force, weak force, and electromagnetic force are all manifestations of one interaction at extremely high energies. A prediction or an analogy that can explain this phenomena is the proton decay. Many theories predict something astonishing. The proton is not truly stable. Given an unimaginably long time, it could decay into lighter particles. Experiments have searched for proton decay for decades so far. No confirmed proton decay has ever been observed. This has ruled out several grand unified theory models, but not all of them. Moving towards the stage 4, the electroweak era. Around 10 per minus 12 seconds from the Big Bang, the temperature was at around 10 per 15 Kelvin. The electroweak force finally splits into the electromagnetic force and the weak nuclear force. This isn't just an idea, it has been experimentally confirmed. Higgs field's rule. Before symmetry breaking, particles behaved as though they were massless. As the universe cooled, the Higgs field acquired a non zero value everywhere. The particles interacting with the Higgs field gained the mass. This change helped split the electroweak force into the electromagnetic force mediated by the massless photon. Without the Higgs field, there would have been no stable atoms, no chemistry, no stars, no planets, or no life. So, what are we today? Today, the universe has four distinct forces: gravity, electromagnetism, the weak, and the strong nuclear force. They appear completely different because the universe is now far colder than it was in its first fraction of a second. There is another interesting part of this theory, the quantum gravity. The first three non gravitational forces are successfully described by the standard model of particle physics, but gravity is not. This is the biggest gap in our understanding. To truly unite all four forces, physicists need a theory of quantum gravity. Some leading ideas include the string theory. Fundamental objects are tiny vibrating strings rather than point particles. Different vibration modes currents corresponds to different particles, including a quantum carrier of gravity called the graviton, or also another theory of loop quantum gravity, which suggests that space itself may be of tiny discrete loops, suggesting spacetime has an atomic structure. Neither theory has yet been experimentally confirmed. Coming towards the theory of everything, a true theory of everything would describe gravity, electromagnetism, strong force, weak force. Using one of the mathematical framework, it would explain why these four forces exist, why their strengths are different, why particles have the masses they do, why the universe has the structure we observe. It could connect quantum mechanics with general relativity and reveal what happened at the very beginning of the cosmos. A final thought to put forward: every force we have explored, gravity shaping galaxies, electromagnetic lighting the stars, and the strong and the weak force binding nucleus and carrying the functions inside the sun, may be echoes of just a single elegant interaction that existed when the new universe was just unimaginably young. The quest for unification is more than just solving an equation, but is an attempt to answer one of the profound questions: was the universe at its deepest level built from one simple idea? If the question is answered, it may become one of the greatest scientific discoveries in human history.